Welcome to the DSP Builder Advanced Blockset Getting Started online training. My name is Carl. In this presentation, we'll introduce you to the DSP Builder Advanced Blockset and its basic usage inside the Mathworks Simulink tool to generate RTL for the Intel Quartus software. This training is part of a series of trainings on the DSP Builder Advanced Blockset toolset. We will begin with an introduction to the DSP Builder in the context of using FPGAs for your DSP design. Then we'll move on to how to get started using the DSP Builder Advanced Blockset. There are many reasons to leverage FPGAs for DSP processing. FPGAs provide a reconfigurable solution for implementing DSP applications. FPGAs allow a specialized solution with custom hardware, allowing you to construct the architecture, memory, accelerator, and DSP blocks needed. FPGAs can also be configured to operate in different modes with different functionality. The embedded DSP blocks on FPGAs provide functionality such as addition, subtraction, and multiplication, and other common arithmetic operations in DSP functions. The DSP blocks on modern FPGAs are variable precision, meaning they can operate in different modes such as standard precision, high precision, or even floating point mode. Your DSP hardware can also be easily integrated with an embedded processor such as the Nios 2 soft-core processor that can be synthesized into the FPGA, or be controlled by an ARM processor that's on the same die as the FPGA in our SoC products. Overall, FPGAs provide throughput and efficiency for your DSP applications. The DSP blocks on modern FPGAs are flexible and powerful. They can be configured into different modes that offer different precisions of fixed point multipliers. They contain adders with accumulation, internal coefficient register banks, and different rounding and saturation modes. There are pre-adders to form tap delay lines for filters, and they can even be put into single precision floating point mode, which allows IEEE compliant operations. There are up to thousands of DSP blocks on each FPGA, which makes it ideal for DSP applications. The DSP Builder for Intel FPGAs is a high-level tool that enables Mathworks Simulink to generate FPGA RTL hardware. The DSP Builder is a collection of device-optimized Simulink blocks which allows you to build and verify the DSP model you need, and then at the push of a button, generate an RTL implementation of that model that can be easily integrated into the Intel Quartus software to be compiled into a FPGA bitstream. In the Simulink tool, DSP Builder enables high-level design exploration of performance and resources. It allows verification through Simulink as well as automated model sim simulations, and there's the ability to speed up simulation using FPGAs through hardware in the loop. Traditionally, DSP FPGA systems are developed in three different stages: development, implementation, and verification. In the development stage, a system-level simulation model, usually written with MATLAB by the system engineer, is created to help define the algorithm. After the development stage, the algorithm and specs are passed along to the FPGA hardware implementation team. There, the algorithm is coded in RTL and often leverages instantiations of DSP-related IPs. The implementation stage uses hardware synthesis tools such as Intel Quartus Prime software, Mental Graphics Precision Synthesis, or Synopsys Simplify software. Lastly, the implemented module is integrated with the rest of the system and tested by the verification team. Each stage is an iterative process, and usually the algorithm has to be passed back and forth a couple of times before the product is finalized. This over-the-wall approach is error-prone, makes for disjointed verification, and last-minute requirement changes are difficult to handle. With the Intel DSP Builder design platform, the same Simulink model can be used to refine the algorithm and generate RTL code. Furthermore, various on-chip debugging capabilities can be built into the same Simulink model and be used in the verification process. The same model can be used in all three different stages to minimize mistakes and increase the overall productivity. With DSP Builder, engineers can implement and verify the algorithm in Simulink, generate the RTL for the model in Simulink, which becomes the implementation, explore design trade-offs, and verify functionality in ModelSim or Simulink. The generated RTL can be easily integrated into the Intel Quartus tool for compilation into FPGA bitstreams. A single Simulink representation can be used in all stages of the design, minimizing problems and significantly increasing productivity. The DSP Builder for Intel FPGAs is part of several tools which allow high-level design for Intel FPGAs. For the software developer, you can use the embedded design suite for our ARM-based SoC devices. There's the OpenCL SDK, which allows you to quickly accelerate algorithms on the FPGA using the OpenCL infrastructure. And then there's the HLS compiler, which can generate RTL code from C or C++ code. With DSP Builder and HLS compiler, they are front-end tools that produce RTL to be integrated with the rest of an FPGA system and compiled by the Quartus Prime design software. The DSP Builder Advanced Blockset does not interface directly with the DSP Megaphone functions, but instead includes its own timing-driven IP blocks that can be used to generate high-performance FIR, CIC, NCO, and FFT models. You can build from a ready-made IP library which contains filters and waveform synthesis components, or you can build a custom DSP IP from the primitives library. The primitives library has vectorization support, contains an algorithmic block, meaning you would build depends on the algorithm without worrying about the actual latency. And DSP components can also be easily integrated into the Quartus tool through the platform designer or RTL instantiation and can be integrated with a processor for control as well. There's automatic pipelining and resource sharing support, meaning depending on the sample rate, clock rate, and the device specified, the tool will automatically vectorize, resource share, and pipeline to construct the smallest circuit that can meet your performance needs. You can create custom interfaces through memory mapped and streaming Avalon interfaces that interacts with other FPGA components, and you can easily design and explore across families, comparing resources and performance differences. The DSP Builder allows you to focus on architecture rather than implementation and generates the RTL for you. The DSP Builder is essentially a collection of device-optimized DSP building blocks. We call this the Advanced Blockset as compared to our legacy product, Standard Blockset, and are separated into 5 different categories. The design configuration block contains blocks that controls the performance and the target devices as well as the generated files of the Simulink model. The interfaces blocks allows you to create the custom memory mapped or streaming interfaces for your DSP model. The IP blocks are full IP functions, including filters, waveform generation blocks, and FFTs. The primitive blocks include blocks of low-level functions that can be used to create custom functionality in a primitive subsystem. There are basic math blocks, logic blocks, and FFT elements. Lastly, the utility block contains miscellaneous functionality, including channelizer and dechannelizer. These blocks can all handle vector and complex data types. The DSP Advanced Blockset libraries are technology independent, but the generated RTL is FPGA and speed grade specific. This means the implementation in Simulink stays the same for all device families, but to generate device-specific and optimized RTL, all you need to do is set the target device family with the device block, and the tool automatically handles using resources in the target device to meet your specific Fmax requirements. This also makes design exploration easy. The data path that's generated is automatically timing driven, meaning you specify the frequency and the tools will optimize based on your specified device and specifications. DSP Builder can pipeline and insert registers into the data path to improve Fmax. It can perform algorithmic retiming to move registers from different areas of logic to balance pipeline. It can manage bit growth or fixed point designs and automatically perform multi-rate optimization, which optimizes the hardware at different places of the data path based on the sample rate at that specific location. When what you need to build is not in the IP library, you can build your own custom IP systems using primitive blocks. When building the primitives model, you can use textbook-based design entry, which is cycle-accurate at each step, but this is more difficult and not recommended. Instead, you can leverage vector support and zero latency blocks, which means blocks are behavioral in nature. Zero latency means each block in the primitive system is treated as an algorithmic block with no delay, but the actual latency is added when we generate the RTL to meet performance needs. This method results in a much simpler schematic, meaning you can focus on what each block does and not when it does it. You focus on signal flow while the tool handles vectorization. This makes it easier to debug and modify your model so you can design once and retarget to different families and speed grades. For FFT designs, you can build using complete FFT IP functions from our FFT IP libraries. This library includes the FFT, FFT float, VFFT, VFFT float, bit reverse core C, and variable bit reverse blocks. With primitives, you can also build custom FFTs from the FFT element library. Use these library blocks to support FFT designs, and it also includes several blocks that support Radix 2 algorithms, which is a serial version of the Radix 4 architecture. The contents of the FFT element library are listed in the table on this slide. Please see our example designs, which show you implementations of the FFTs using either method. In the DSP Builder IP library, there's also comprehensive channel filter and waveform synthesis support. The IPs here include various types of finite impulse response filters, including cascaded integrator comb filters, mixers, and numerically controlled oscillators. The IPs here support automatic resource sharing based on sample rate, if the sample rate is lower than the specified frequency, and also support super sample rate architecture with automatic vectorization. The DSP Builder blocks automatically infer hardware from abstract data types. This means the IP architecture generated are optimized for complex and floating point data types. We support scalar, vector, complex, fixed point, and various standard and non-standard floating point precisions. DSP Builder can also automatically channelize hardware generation from input vectors coming into the model. DSP Builder fully supports supersample designs, where the sample rate exceeds the FPGA frequency. Support includes FFT and FIR IP with supersample rate specific architectures. The basic primitive blocks will automatically replicate as needed, and all Datapath hardware generated supports supersample rate designs. As an example, if the ADC source coming into the FPGA is producing 8 gigasamples per second of data, while the DSP datapath on the FPGA runs at 500 MHz, then the supersample rate datapath will create the 16 lanes of processing automatically, aligning the data. For primitive subsystems, DSP Builder also supports ALU folding, which significantly improves area efficiency for low throughput designs. If the folding factor, which is the clock rate divided by data rate, is greater than 500, then the primitive subsystem can be set with ALU folding. With ALU folding, all resources are aligned in the ALU-like fashion, so the same resources can be reused for maximum utilization. As illustrated by the diagram, the DSP Builder will automatically generate the finite state machine, which can share the multiple resource among 3 different data paths, A, B, and C, in a time division multiplexing fashion. DSP Builder also has a system-in-the-loop hardware verification feature that allows you to validate generated hardware on an Intel FPGA development board for faster verification of generated IP with the original Simulink model. This feature allows you to run Simulink simulation while the model executes on the FPGA with automatically generated hardware verification system. Users can also use this feature on third-party or custom boards if they set up the board support packages for these boards. Lastly, the generated component from Simulink with the DSP Builder Advanced Blockset is fully compatible with the Intel Quartus tool as well as Platform Designer. Interfaces to and from the model can be easily connected via memory mapped, streaming, and conduit interfaces to other FPGA components or I/O interfaces. You can also connect with processors and state machines that can control the properties of the DSP system, for example filter coefficients. The DSP Builder generated IP also supports design reuse, so you can instantiate it multiple times in the same or different FPGA projects. Now that we understand the basics of the DSP Builder tool, let's get started with using the Advanced Blockset. Here we'll talk about installation requirements, the Simulink environment, how to create models, the design hierarchy of DSP Builder models, device configuration blocks, and then the running of the Simulink simulation. The DSP Builder for Intel FPGAs integrates with the Mathworks MATLAB and Simulink tools with the Intel Quartus Prime software. This slide lists the tool dependencies for the DSP Builder. First, ensure MATLAB and Simulink tools is available on your workstation before you install DSP Builder. You will need a compatible version of MATLAB. Check the DSP Builder software requirements webpage for exact versions of compatibility. Quartus Prime software of the same version needs to be installed prior to DSP Builder as well. Lastly, if you plan to take advantage of automatic RTL simulation features of DSP Builder, you also need the Mentor Graphics Model Sim or Model Sim Intel FPGA Edition software. All tools need to be appropriately licensed. MATLAB is a high-level technical computing language and interactive environment for algorithm development, data visualization, data analysis, and numeric computation. You can use MATLAB in a wide range of applications, including signal and image processing, communications, control design, test and measurement, financial modeling analysis, and computational biology. Add-on toolboxes extend the MATLAB environment to solve particular classes of problems in these application areas. Simulink is a MATLAB-based environment for multi-domain simulation and model-based design for dynamic and embedded systems. It provides an interactive graphical environment and a customizable set of block libraries that lets you design, simulate, implement, and test a variety of time-varying systems, including communications, control, signal processing, video processing, and image processing. With MATLAB and Simulink, you can generate a validated design that feeds into other hardware and software tools, such as the Intel Quartus Prime software for FPGA hardware generation. You can execute MATLAB commands and set variable values via the command line, but this is not efficient for common or frequent operations. For reuse, MATLAB supports a scripting language. Create a MATLAB.m script file to execute the same commands that you will enter on the command line. One of the most common uses of .m file is setup and initiation of Simulink models. MATLAB.m files can be executed from the command prompt, from the Run button in the text editor toolbar, or directly from another script. It's important to know that any setting or parameters set in the script becomes part of the workspace, and the .m script has access to all settings or parameters in the workspace. With Simulink, you can design systems in a schematic fashion. Simply create a model and use the blocks from Simulink libraries, including the DSP Builder library. You will then be able to graphically specify time-dependent relationships among inputs and outputs. After you've done specifying the model, you can use the Simulink to simulate the block model by specifying the start and end times and providing stimulus. The Simulink tools has a library browser that contains supported blocks, including the DSP Builder Advanced Blockset. Within the library browser, you can navigate through the blocks in different libraries and use those blocks by simply drag and dropping the blocks from the library browser into a Simulink model file. In order to use DSP Builder Advanced Blockset, you'll need MATLAB, Simulink, and the Fixed Point Designer add-on. The DSP Builder Advanced Blockset uses Simulink fixed point types for most operations, which is why that's required. We also recommend licenses for the DSP System Toolbox and the Communication System Toolbox, as well as the Signal Processing Toolbox, which many of our design examples use. If you don't have licenses for the tools available yet, evaluation licenses for Simulink and MATLAB for use with DSP Builder can be obtained from Mathworks by following the link provided here. In order to be sure all of the correct paths and libraries for DSP Builder are captured, be sure to launch MATLAB from the script provided after DSP Builder is installed. To begin a DSP Builder project in Windows, start MATLAB using the link provided in the Windows Start menu under the desired version of DSP Builder. On Linux, start MATLAB using the DSP Builder.sh script, which is in the DSP Builder Advanced Blockset install directory. To point to the correct version of MATLAB, use the -m option to specify the MATLAB path. Once MATLAB is running, you can create or open the Simulink model. First, in MATLAB, set the working directory to where the model files .mdl or .slx are located. Open the Simulink library so you'll be able to add DSP Builder or other blocks into the model. Lastly, from the Simulink library or MATLAB main window, either use the New option to create a blank model or Open option to open an example model or a saved model. The easiest way to start a new DSP Builder model is to use the New Model wizard from the DSP Builder menu. Once you have an existing model or blank Simulink model open, use the DSP Builder menu to choose the New Model wizard. Inside the wizard, you can select a fixed or floating point model. You can select a type, simple with channelizer, enter the model name, and select where to save the model. When all the parameters are set, click the Generate button and close the dialog box. Once the generation has finished, you'll see a template model with the appropriate test bench created. Once you created or open the DSP Builder model, you'll see the top-level Simulink test bench. For new models, the New Model wizard automatically creates top-level test bench denoted by the control blocks with Simulink components placed for input and outputs, allowing the model to be simulated right out of the box. This way you start with a known good testbench environment to build from. Also, it produces a MATLAB.m file so you can easily parameterize each component of your model without having to find each one and edit it manually. We'll talk about this in a little bit. With example designs, you'll be able to navigate up and down the hierarchy to explore the components. With the new models, you'll see a blank DUT placeholder. Navigate into it and start placing blocks in it. The figure here shows the top-level design, synthesizable system, and model primitive subsystem relationship, as well as the required blocks. The required blocks are colored orange. At the very top level of your Simulink design, there needs to be a DSP Builder control block, which is used to specify generation options as well as clock frequency options. The top level is also where testbench components are located, for example, to grab input data and display scopes. Below the top-level testbench is a synthesizable design. Everything this level and below needs to be synthesizable for the FPGA. The synthesizable top-level design is marked with a device block where you can specify target device family and speed grade. Other IP functional blocks can also be placed here. To build a primitive subsystem, the synthesis info block needs to be specified, which tells DSP Builder the mode of the subsystem and latency options. Primitive subsystems can only contain primitive blocks and are always bounded by the channel in or GP in blocks at the input and the channel out or GP out blocks at the output. Of course, there can also be many other types of hierarchy as long as the rules are followed, where non-primitive subsystems can include IPs and primitive subsystems, while primitive subsystems can only contain model primitive blocks. The DSP Builder blocks are separated into different categories. In this training, we'll examine the design configuration and utility blocks. In follow-on trainings, we'll examine the interfaces, IP, and primitives libraries. The design configuration library includes many FPGA RTL generation-related blocks. The control block specifies information about the hardware generation environment, including clock and reset parameters. It must be present at the top level of the model. The device block marks a particular Simulink subsystem as the top level of a synthesizable FPGA system. This causes the tool to generate project files and scripts that relate to this level of hierarchy. The Avalon Memory Map Slave Settings block customizes the Avalon Memory Map Slave interface exported by DSP Builder Advanced for any model bus blocks in your design. And lastly, the local threshold block allows hierarchical overrides of the global clock margin and threshold settings on the control block. The control block, required at the very top level of the model, traverses your design, synthesizes the individual model primitive or model IP blocks into RTL, and maintains an internal data flow representation of your design. Simulink simulation uses the internal representation of your design and writes out the RTL and scripts to other tools. DSP Builder applies globally the options in the control block to your design. On the General tab of the control block specifies information about the hardware generation environment. You can specify whether RTL code should be generated and where it should be placed. On this tab, there's also the hardware resource trade-off section where you can influence the multiplier and memory resources each block uses. The tool will examine each block in the system and perform resource trade-offs based on the threshold values. With the memory threshold, you can decide whether to implement memories out of dedicated RAM blocks or use logic elements. Similarly, with the multiplier threshold, you can choose to use the dedicated hard multipliers or the soft multipliers built from logic elements. On the Test Benches tab, if you want, you can choose to enable the automatic test bench flow. When the flow is enabled, test benches and modelsim.do files are created for each block, and also the input and output of each blocks are captured. The modelsim.do files can be invoked from command line to compare Simulink simulation results with RTL simulation results. On the Test Benches tab, you can also specify whether or not to import modelsim simulation results back into MATLAB. With the control block on the Clocks tab, you can also specify the details of the clocks and resets that drive the generated logic. The DSP Builder Advanced Blockset uses a single system clock to drive the main logic. Here you can name the clock, and reset signals the RTL uses, and also provide the clock rate, which is used by the tools to calculate the ratio of sample rate to clock rate, which determines the amount of folding or TDM and vectoring for model IP components. The clock frequency and clock margin fields, which is the additional timing slack, are also used to determine the pipeline required at each stage of logic. For example, the design may modify the amount of pipelining that hard multiplier uses and pipelines long adders into smaller adders based on the absolute clock speed in relationship to the FPGA family and speed grade you've specified in the device block. In an advanced block set design, the synthesizable portion of design is always separated from the Simulink stimuli and contained in its own subsystem, marked by the device block. Each subsystem within the synthesizable subsystem block denotes an additional hierarchy in your design. We can navigate these by simply double-clicking on the component or navigate from the model browser window. In the device block, you specify the device family, optionally the target part within that family, and the speed grade. This causes the tool to generate project files and scripts that relate to this level of hierarchy. All blocks in subsystems below this level become part of the RTL design. All blocks above this level of hierarchy becomes part of the test bench for the synthesizable subsystem. Multiple device blocks in non-overlapping subsystems may be used to signify multiple FPGAs IPs will be created for the current model. In that case, even multiple FPGA families may be mixed across top-level synthesizable subsystems. The model primitive blocks are low-level functions that can be used to create custom functionality in a primitive subsystem delineated by the channel in, channel out, or GP in and GPL blocks. Few of these primitives can also be used outside of model primitive subsystems as glue logic. We will talk more about how to use these blocks in a follow-on training. The model IP blocks are full IP functions provided by the DSP Builder that can be added to your synthesizable subsystem outside of model primitive subsystems. The IPs provided include various types of finite impulse response filters, including cascade integrator comb filters, mixers, and waveform generation IP, such as numerically controlled oscillators. The IPs here support automatic resource sharing based on sample rate, if the sample rate is lower than the specified frequency, and also supports super sample rate architecture with automatic vectorization. The interfaces blocks allows you to create custom memory mapped or streaming interfaces for your DSP model. In the memory map section, there are memory map registers, bits, external memory blocks, and stimulus blocks. The streaming section contains Avalon streaming input, input FIFO, and output blocks. More about these will be discussed in the follow-on training. The Utilities library in DSP Builder contains miscellaneous blocks that supports building and refining designs. Inside Analyze and Test section are blocks that help with design testing and debugging. For example, the Capture Values block can capture a variable number of signal inputs and support vector and complex types. The Pause block implements a breakpoint with trigger count to break and single step through Simulink simulations. The Channelizer and Dechannelizer blocks are used to channelize and dechannelize simple multi-channel matrices to and from the DSP Builder valid channel and data protocol. The Display Resources block displays the resource estimates at the block subsystem or system level. And finally, the Edit Params block provides a shortcut to the parameterization MATLAB script file named setupModelName.m. This file can be used to store various information about the model, such as sample rate, clock frequency, simulation parameters, filter coefficients, etc. It's recommended to use this script file to create variables, and then in block instantiations, just refer to these variable names. If you use the new model wizard to create your model, then the script file is automatically created for you. In order to properly update your MATLAB variables, you will need to execute the MATLAB setup script from the previous slide before performing the Simulink simulation. It's recommended to create callbacks to run this .m file. When you use the new model wizard, the callbacks are automatically set for you. The two important callbacks to use to load the .m file are the preload function, which runs the script when the model is opened, and the init function, which runs the script just before Simulink is run. If you create your own additional setup script, you can also add them to the callbacks using Model Properties callback tab shown here. In Simulink, the DSP Builder menu should appear on all model windows. Use this menu to start all the common tasks you need to perform your DSP Builder model. Here you can create a new design using the new model wizard, create a system in the loop setup for hardware co-simulation, run verification on your Simulink model, parameterize your control Avalon interface to configure the memory map interfaces to your processor or state machine, see the estimated resource consumption, see the current memory map, as well as to run the model simulation or to start a Quartus Prime project. The options in the DSP Builder menu makes it easy to verify and visualize the DSP model you've created. Once your model has been built, you can run the Simulink simulation on the model to verify the system in simulation. If HDL generation has been enabled in the control block, running the simulation will also create HDL code for the model based on the settings in the model. It will figure out pipelining and latency necessary to meet the frequency specified and create a synopsis design constraint file to ensure it makes timing during place and route phase of the Quartus FPGA compilation. The generated files will be located in the folder specified in your control block, with each synthesizable subsystem marked by the device block having its own subfolder. In addition to the HDL files, other files such as QIP files to integrate with the Quartus Prime software and the hardware.tcl file which describes the component to the platform designer are also generated. Each time you simulate, past generated files will be overwritten by new ones. After you've generated DSP Builder model in Simulink, in the RTL directory, you will see all the files necessary to integrate with Quartus tool or the Platform Designer System Integration tool within Quartus. To integrate your IP inside the Platform Designer within the Quartus software, add the generated file path to the Platform Designer IP search path. After that, your Advanced Blockset system will appear in the IP catalog library, where it is ready to be added to your Platform Designer system and connected to other FPGA IP, including interfaces and processors, and can be generated and synthesized by the Intel Quartus software. In this screenshot, you can see the generated complex FIR DSP Builder model in the library. It is also already instantiated in the System Contents tab and then connected to a Neos 2 processor that's being used to interact with the complex FIR. This concludes the online training. To summarize, in this training, we covered the basics of the DSP Builder tool and explored how to get started using the Advanced Blockset to quickly create, verify, and generate RTL for your Simulink model. I have also included here links to additional resources regarding Intel FPGA DSP usage. Go to the DSP Technology Center, which contains DSP Builder documentation, device guides, DSP IP guides, app notes, reference designs, and release notes. You may also visit DSP Support Center, which is the DSP Technology Support landing page. One last thing, when you register for this training, a link to a short online survey was sent to you in your confirmation email. Please complete the survey to let us know what you think of this training. Thank you very much again for attending the DSP Builder Advanced Blockset Getting Started online training, and best of luck with all of your designs.